welcome Ofer Lahav from UCL, who's going to talk on dark energy observational probes.
Thanks very much, Anne. Good morning. Thanks to organizers for the invitation and for a great meeting. Apologies for missing a couple of days due to UCL commitments, including missing the banquet. So months ago, I gave the title Observational Probes and Alternative Models. Then I realized in the program several distinguished theoreticians are speaking after me about alternative models, so I leave most of it to them. And I thought I'll focus more on the observational probes, especially one of the surveys I'm going to talk about is the Dark Energy Survey. And the telescope is shown on the right there, where actually we started the survey this week. Some of you might have seen the press release. So this is quite a special week for us. Just to summarize, we heard a lot about the status of cosmology at present, mainly driven by Planck. I'd like to talk on something which perhaps does not get enough attention, which I find quite interesting, to look at, do we see dark energy on megaparsec scales? Touch on that. Then, rather than describing in 5 seconds each of the projects around the world, I thought I'll focus on 2 projects which are kind of fairly generic in their nature and can indicate to you, especially perhaps to the theoretical part of the audience, the way it's actually done. And the one is the Dark Energy Survey. The second is, which is an imaging survey. The second is the Dark Energy Spectroscopic Instrument, which is a union of Big Boss and DESPEC. So we've got now DES and DESI. My 4-year-old daughter asked me, is DES a man and DESI a woman? You know, it's a bit confusing. I think I'll say DES when I mean DES and DESI when I mean DESI. Combined probes and maybe a bit speculating about the future. So we heard a lot about this, the known unknown, 95% of the universe. I think the George and Joanna gave excellent talks about the improvement due to Planck, although no big picture hasn't changed. The way we do it as observers, we obviously have probes, and they're listed here. Many of them already being discussed. And really mathematically, what it is that each probe has its own physics. And this is a probe of clustering, which is what most those probes are. Has its own physics and setup, observational setup. So in galaxy survey, it would be the number of galaxies with redshift. And the power spectrum comes here. So basically, we are interested in the power spectrum, and these are the window functions. So that's what we do. And that's when you have 2 different probes. You can do cross correlation. If you have just one probe, it's an autocorrelation. And basically, what this manifests are 2 physical effects, the geometry and the growth of structure. I'll mention in passing, this will come later, that I think the future seems to go now in the direction of cross correlations. So a cynical view is, if you have probe A and you got bored with it, and you have probe B and you got bored with it, what do you do next? You do A cross B. But I actually think there's more to it. And there's a lot of power in it. We've seen it, some illustrations in the CMB talks that day. So what is dark energy? Certainly in the MTP, no need to write again this equation, but it's good to remind ourselves that assuming it's something like lambda, there's still a freedom of putting it on the left-hand side, and you can call it modified gravity relative to what it was before Einstein put it there, or you can put it on the right-hand side and absorb it as T mu nu. And I think this is the generic problem of, is it something, a modification to the underlying curvature, or is it actual stuff? In every cup of tea, there is a bit of dark energy, right? That's kind of, I think, the question. Now, there's a long list of options there, already discussed this week. Is it just systematics? Is it lambda CDM, dynamical scalar field, signatures, modified gravity in homogeneous universe, anthropic principle? I'm not sure I'm allowed to talk about it here, but maybe. Something else unpredictable. George, as I walked in, George said, but we know W is -1, so let's take a vote. I said, how do you know? In a longer talk, I'll probably go one by one, but then the chairperson would not be too happy. So how many would vote it's just lambda? George, look around. It's not everyone. It's not everyone. Why I misquote? Right. Okay. Okay. How many people think is something completely different, which we haven't even thought about? Okay, that's silence there. All right. I should also mention, it's quite interesting, the reflections of the community to the Planck result. I believe correct me, George, I believe the ESA press release said an almost perfect universe, which I still have a hard time understanding what it actually means. The New York Times, I think, was a bit more, I think, more perceptive in my view, a simple but strange universe. So here we are. In terms of results, lots has happened in terms of galaxy surveys. The Sloan obviously produced lots of good data, and BOSS is a kind of follow-up of this. It's spectroscopic, so here you can see the correlation function against separation with a remarkable peak. This is the baronic acoustic oscillation, then translated into W, constant W and omega m, and adding CMB at the time, it's pre-Planck, you can see that it zooms in quite nicely on the minus 1.3, plus minus 0.7, so kind of in accord with later what Planck plus have found. One important remark here, that's the point people say, look, we're moving to work on exoplanets. I mean, this is cosmology solved. But remember, this is for an assumed constant W. It's an assumed constant W. The moment you relax that, if you read carefully the tables in those papers, you see arrow bars on the time derivative of W to be of the order of 20%. This is another very nice illustration from Chris Blake. The Australians have done this project called Wiggle Z. And what's nice here is it's basically Hubble diagram, so it's quite intuitive. Redshift here and distance, except that now we know distances through BAO. So these are the supernovae scattered all over. Sloan, these are black lines, and the Wiggle Z. I'd like to draw your attention to kind of a new technique, or a technique which is, I think, has matured now, to actually use the Lyman alpha clouds. So these are clouds between us and the quasars. And because we have many, many lines, we can actually use it to do BAO. So that's kind of a new technique. So Redshift 2, we actually have that result. Of course, acceleration happens below Redshift 1, but it's good to see that continuity. So I think that's quite nice. A new, well, I can't say new technique, because I remember late 80s when I was a PhD student at IOA, Nick Kaiser worked it out. So it's not all new at all. This is the redshift distortion. So what happens is redshift is not distance, there are peculiar velocities, especially around clusters. You could see an infall, that's onion pattern here. There's also finger of God. And basically means you see gravity in action. So this is the fluctuation galaxies, this is the bias parameter. This is this growth factor, logarithmic derivative of fluctuations with respect to time. And this is the mass fluctuations, and this is just the cosine of an angle. This is one parameterization of modified gravity. It goes back to Jim Peebles in the late 70s, famous formula 0.6, and then there have been many, many iterations on that. And for example, modified gravity models will give a different number. So one question, which hopefully might be discussed later, is this a good parameterization for modified gravity? In any case, this is this growth against redshift proof of concept. You can really see gravity with time, with cosmic epoch. It's very exciting. And you can already rule out some funny models, say DGP, for example. The nice thing here, if you look at this equation, I should have put mu on that side as well. It's parabolic in mu. So in principle, you can solve for B and F independently, free of biasing. If you just do it as look at the angular pattern. But it's linear theory. This has to be said, linear theory. Now, again, leaving it to the wise speakers after me to map a pretty large zoo of modified gravity. What's a non-elephant? That's not easy to say. But this seems to be popular, okay? As a phenomenologist, I seem to get the impression this is quite generic, where you relax the idea to have two potentials actually in the metric, not only one. not assuming they're equal. And then the different parameterizations in the literature. This one has Q and R. I'll show an example of that. R basically is the ratio of two potentials. So when it's exactly 1, we're back to the standard GR, which gives the factor of 4 in the deflection of light around the sun. And then there's this Q, which modifies Poisson equation. But then, you know, it can keep many people happy. You can make Q and R functions of redshift, and you can put it into MCMC, and we get a big industry and spend 10 years trying those different models. What's interesting here, because I said one theme of this talk is cross-correlations. What's very interesting is that cosmic shear, and for that matter anything which describes the trajectory of photons, depends on the sum of those two potentials, psi plus phi, while galaxy motions only depend on on psi. So you have nice complementarity here. You can, in principle, tell one from the other. And this has been an active area for research. Now, if I may, 1 minute to allow myself to be a bit philosophical about it. I find when I talk to funding agencies, in fact, we had a presentation yesterday to STFC about a new project called DESI, respecting members of the panel and so on. The moment you talk about dark energy, modified gravity, it does sound science fiction to people who work on planets or on particle physics. But I think it's interesting, and likewise when you give public outreach talks, I find it quite interesting to think about it. It's really, we're down to the point that when observations disagree with a model at a time, there are logically two possibilities. Well, first there's a possibility that data are wrong, but let's assume that's okay. Two possibilities: either you add something, an entity, or you modify the theory. Now it's quite nice because in the solar system we've got those both examples. Right, Neptune, which was nearly discovered in Cambridge, predicted there based on unexplained motions of Uranus, right? So the wobble of Uranus indicated to clever mathematicians, Adams here, that should be another planet there. And then it was discovered. That's a beautiful example. Think of it as dark matter. Then, on the other hand, Mercury, of course, we know the explanation comes through GR. Incidentally, you may know that actually people suggested another planet, a Vulcan, to explain that, and this turned out to be wrong. So I think we're in the same situation with dark energy. I'm actually collaborating, as a bit of entertainment, with a philosopher of science, Michele Massimi from Edinburgh, looking at some cases in physics and astronomy. So we mentioned those two. Beta decay, again, you either come up with a new particle or you violate the theory. So brackets is what didn't work, like Vulcan and violation of conservation. Galaxy flat rotation curves, we still don't know. Is it dark matter, which is what the majority of people think, or is it a tweak to gravity, Milgrom-Bekenstein's relations? And accelerating universe, we're there, right? We don't really know what it is. So I think it's quite interesting to think conceptually you have those two options, and it's our job to explain it. Now, I would like to, I find, it's kind of interesting. The observer seems to zoom in for a constant W on -1, and yet theoreticians have actually expanding the parameter space. I only show the very modest parameterizations. There's now other parameterizations like the Hordensky, Lagrangian, things like that, which are a bit scary. Many, many parameters. So I'm just looking for something that I can actually understand. Okay, so this comes to the question: what happens to a bound system? Okay. So in a simulation, N-body simulations, what happens is you just put 1/r², and the box itself is expanding. But when it's a bound system, LTB, Lemaitre, Tolman-Bondi, that's an exact result. That actually you can see it as a sphere. Imagine a sphere collapsing. There's -gm/r², and then the addition of r. So it looks like Newtonian. Right? And it almost feels like Newtonian, and it's the right place in Cambridge to mention that Newton actually has got a linear force as well in his Principia, except he didn't put λ/3. John Barrow has written articles together with a student, Lucy Calder. We also wrote an article about this, just elaborating. But in any case, this is the equation we're using. This is the equivalent energy equation. So then you can take the view that if you know certain parameters, you can, for example, tell the mass of the system or tell lambda. So it's the usual statement is, what we tell students, look, it's cosmological constant, so we have to go to redshift 1 to do it. But can we do better? So on spherical collapse, there have been studies along these lines, even before the supernova studies. One discovery from me this conference, talking to Anthony Lazenby, that his group has written 3 papers, actually, past year on elaborating on this, connecting it to GR, papers I still like to study. So that's the theory. Now, what happens in practice? How could you actually measure it? So there is a very old argument called the timing argument, Cannon-Volcher, 1959, which was then expanded by Lyndon Bell in the 81, but it doesn't take lambda into account. So I asked myself a naive question when a master's student looked for a project, Candice Partridge, what if we just take the classic timing argument? So timing argument is that you have Andromeda and Milky Way at the same place. At the beginning, the universe expands, but they collapse, and if it's on a first collapse, their distance separation, their inflow velocity, so you can play with that very simple equation there and actually get the mass. In fact, I think this argument is somewhat not sufficiently credited for being one of the first to indicate the dark matter problem. So this was the question. After we kind of answered it, I then discovered that there's some papers by Chernin and even a problem in Bini and Tremaine on that. But what's remarkable, if you put the latest numbers, including Planck and those numbers, it makes a difference of 13% to the mass. So I would put it this way: the dark energy is visible on megaparsec scales. It makes 13% to the mass. Now people say, well, but that's a naive model. These are point masses. Use simulations. So we've done that using simulations called clues. And it turns out, so red are those in the old, sorry, blue are with the old model without putting lambda, red is with lambda. But bottom line, it brings it closer if you put the lambda in. But we can also use the simulations just to calibrate for other effects which we don't count in this simple model, such as tidal forces, for example, and other neighbors. Yeah. Bottom line, the number to take home, we find that our estimate for the virial mass of the local group is about 5, 10 to the 12 solar masses. So anyway, to me, it's kind of an interesting indication of lambda on smaller scales. Moving to surveys, that's a very big area now. Broadly speaking, it's divided into photometric and spectroscopic surveys. They're all listed there, including space missions, Euclid, and we heard about the new incarnation of W1 the other day from David Spergel. A lot is going on. As I said, there's no time. I showed some examples from surveys such as Wigglesworth and Boss, just to say that these surveys basically aim at measuring W or deviations from modified gravity, but they'll produce billions of galaxies. And I think, if we know the cosmology at some point, either from God or from a special technique, it's still plenty to do there, and it's not a bad deal. It's about $1 per galaxy. Take all the surveys, how much they cost, how many galaxies. It's $1 per galaxy. So this is a bit putting it on time scale. Again, it's just some examples. I don't pretend to show everything here, but multi-object spectrographs, 2DF was very pioneering in a way, and then BOSS, eBOSS, DESI, Euclid, and the imaging Sloan, Dark Energy Survey, LSST Euclid. So you can see there is this kind of mid-range projects, and then the big ones kick in at about 2020. Okay, the Dark Energy Survey. So this is more or less started 10 years ago. As I said, we actually started a survey this week, on Saturday, in fact. I was very fortunate when after I left Cambridge, 2DF came to an end, and straight after that, together with Chicago, Fermilab, and many other institutions now, we developed this Dark Energy Survey. It makes use of an existing telescope. It's quite remarkable that even use an existing telescope, it takes 10 years to build the instrument. This gives you time scale here. So it's a 4-meter Blanco telescope. The idea is to map 300 million galaxies over 1/8 of the sky, in connection with other surveys that look at the same direction, Vista Hemisphere Survey, SPT clusters. And the idea is to do, it's a multi-probe approach, which at the time, by the way, was quite, when we proposed it, was a bit unusual. Now it's very common if you look, for example, at Euclid. So you look simultaneously from the 300 million galaxies, you create catalog of clusters, and you do weak lensing and large-scale structure, and then with selected fields, you look at supernovae. And I did say, I think, the telescope is in Chile. Oh, so yeah, so first light we had last September, a year ago, and I'll show some examples from that, and the survey just started this week. Again, this is the credits to all the institutions involved. There are 6 universities in the UK, as you can see, plus 4 other nations involved, Brazil, Spain, Germany, and Switzerland. It's about 200 collaborations. Organization of projects probably need attention, not a talk. The director is, founding director is John Peoples, current director George Freeman. Of course, there are instrumentation people, Brenna Flower. I chair the science committee, which has all these different groups with co-coordinators. I just want to emphasize that we have, apart from the core science, we have working groups on, for example, Milky Way science and galaxy evolution. So we don't close our eyes to the possibility that there's other exciting science. This is the footprint. Ignore the red line. This was another possibility, but this would be the footprint, 5,000 square degrees. First year, as of this week, is half the area and about 2/5 of the depth. And we decided to put high emphasis on overlap with SPT because we're quite excited about cross-correlating galaxies and shear with SPT. We'll also do it with Planck, of course, but it's a fertile ground. Vista Hemisphere Survey, Bridget McMahon at Iowa is the PI of this, and BOSS. So that's our proper, and this is the magnitude limits function here, over there. It's quite a massive camera. It's basically weighs several tons. The optics was assembled in our basement. It's my colleague Peter Doll. 5 lenses have to be polished and aligned to half the width of that page. I learned to appreciate what instrumentation people do. It's quite challenging. This is the UCL Provost, by the way, in case you wonder. And here it is. I should say money for this came from STFC, initially 1.7, and from other rich universities, such as the University of Portsmouth. And this is the instrument on the telescope at the inauguration ceremony in November. This is one of the first images. So there are 64 CCDs. If you think it's 570 megapixels, so it's about 100 times more than your typical iPhone camera, okay? But it weighs much more. So that's what you see. And this is just one of the first pointing Fornex cluster. And here's this galaxy. You can zoom in. If you get to the Fermilab website for the press release, you just put an interactive exercise that you can click and see each object, and it tells you what it is. So it's kind of fun. Early data, 7 supernova measured, 5 of them confirmed as 1A on the AAT, by the way, and there's a new project called OSDES to incorporate spectroscopy, a few new clusters, redshift about 0.9, mass reconstruction even, from the lensing around the cluster, mass reconstruction, very preliminary, no hard numbers, and also some work led by my postdoc, Manda Banerjee, of actually contrasting DES and Vista hemisphere survey and combining the photometric redshift, combining the colors to get better photometric redshifts. It's very important to emphasize what type of uncertainty is going to this. One is the theoretical one, right? I mean, how broad is your cosmological model? Do you include neutrino or not? Changes other numbers. Astrophysical, galaxy biasing does in supernova and so on, and instrumental. So we have to deal with all that. This is the photometric redshift game. Remember, the DES is photometric redshift survey, and that's tricky because just from 5 colors and maybe 3 more from Vista, you have to tell the redshift, and it degrades, uncertainty in redshift degrades W by a factor. In other words, you need to know the redshift. if you want 1% in W, you need to know the redshift at the level of 0.2%. Yeah, it's fine. And that's why we need spectroscopy, okay? Shear measurements, cosmic shear is a whole complicated area because apart from the gravitational lensing, you have the atmosphere in the way and a detector and so on. If you like, here is my 1% rule from DS. It's a 1% effect. You want to measure it to 1% to get W to 1%. Okay, so this is the most challenging task. Of course, everything is going to get better. That's all about DES. We'll update you in the future. Of course, along these lines, it's a pretty good idea to put space telescope in space to do lensing. I mean, for example, there's a clash survey for HST that shows beautiful 25 clusters. You can do it almost whole sky, or 15,000 square degrees of the extragalactic sky, 1 billion galaxies, and also spectroscopy. So that's for Euclid. Moving to spectroscopy, there's a bit of history there from just measuring spectrum of a galaxy one by one to doing it as a multi-spectrograph approach. The UK really pioneered some of it. There have been several proposals we didn't quite get off the ground, WFMOS, Big Boss, DESPEC, but the news is that DOE is happy to support now a union of Big Boss and DSPEC, and we just had a collaboration meeting in July. Director is Michael Levy from LBL, and yesterday we made a presentation to STFC. Foremost, which is on Vista, and there's, I know, many people in Europe interested in that, including in Cambridge, and the idea is to do Gaia follow-up, and Rosita Weave is to do, again, Gaia. Samiri PFS, that's a Japanese project on Subaru Euclid I mentioned. And it seems like, you know, just of interest is now cosmology and galactic archaeology. The DESI project will produce, it's using 5,000 fibers, so if you remember 2DF had 400, about 20 million targets over, you know, big chunk of the sky, and the object will be LRGs, luminous red galaxies, emission line galaxies, quasars, and Lyman alpha quasars. That's, as I said, very exciting because you can do cosmology with that. Many different goals here, and there's MCMC machinery, in this case run by Pat McDonald, for the W's and the other parameters that we've seen in the Planck talks. Maybe I'll just draw your attention that it looks pretty promising for neutrino mass, subject to all the assumptions. But to give you an idea, when we did neutrino from 2DF, the upper limit was 1.8 eV. Upper limits before Planck combined with CMB at the time, but mainly from LRG, papers by our group and other groups. BOSS is about 0.25, or let's call it 0.3 EV. Planck, if you take it face value, is 0.23 EV. This is going down by a factor of 10, 0.02. So the easiest way to remember DESI, it's 10 times better than BOSS. Okay, it's got, in terms of fibers, in terms of improvement on parameters, 10 times better. Quickly, should you have surveys, spectroscopy from some part of the sky? This is also a political decision where you put telescopes. Just to mention, there have been quite a number of papers about it. It's all quite interesting. There was a bit of a controversy in the literature of results disagreeing in the range between 1 to 100. So we called a telecon on that. We had a meeting, and I think it's now more converging to the level of little improvement to factor of 2 in figure of merit. This is from work led by a postdoc of mine, Donica Kirk. The idea is to take something like DES and something like DESI, take weak lensing and a large-scale structure. So you see the blue is, sorry, start with the green. Green is just weak lensing. This is W0, WA, yeah? Dark energy figure of merit. Black is the just large-scale structure from the essay. But now if you do both, even if they're not on the same part of the sky, there's huge improvement. And if you do it on same part of the sky, even more. That's the blue one. And you can do the same thing. Sorry, it's not very clear, but this is some combination of these Q and R parameters, which if there are one, is standard GR. If not, you deviate. And actually, for modified gravity, this QR parameterization, looks even more impressive. It's this combination I mentioned that one lensing constraint, the sum of potentials and large-scale structure, only one of them. I'd like to almost finish with two health warnings. One is people do a lot of Fisher matrices, but they don't always give the same answer as MCMC. They don't always give the same answer as MCMC. This is a result from a group in Munich, supernova, so nice ellipses are, for whatever parameters, I won't go into details, nice ellipses are Fisher matrices, second derivatives likelihood, and the funny contours are MCMC. This is from our group, former PhD student Adam Hoken. Again, ellipses are nice, but you can see MCMC for small volumes give different answers. So I think, it's good to do both, of course, but we have to be a bit careful. The other thing, and this was actually a question I asked George at the end of his talk, that I feel comfortable, we're scratching our head. Actually, I have a student, Lucy Calder, who's working on this. How many nuisance parameters are we going to put? Because we're trying to fit the whole universe with 6 to 12 parameters. But then my young, ambitious colleagues who love to run MCMC, they give me a list of 1,000 nuisance parameters, and some of them are correlated with cosmology. So I'm a bit nervous about it. So we're trying to take perhaps a more modest astrophysical approach, for example, for biasing, to find a generic model which agrees with simulations with only few parameters, and try that. This is going to be the approach. There's also some ideas using PCA to compress them a bit. But that's a summary. And so I just want to say, reading of the situation is W constant -1 is not ruled out by the data. Okay, it's at the moment perfectly, I think, especially with Planck, looks perfectly valid. Tell your undergraduates or public talk, it's a pretty good number. But W is a function of redshift, and modified gravity, such like those two potentials, are not yet ruled out. If you like, gravity has not been tested on the very big scales. I emphasize, on the other hand, that maybe there's some scope to learn about it on the megaparsec scale. But there's a lot to come from this service. Just within cosmology, I would say detection of neutrino mass seems to be, we heard it almost every talk, observational talk at this meeting mentioned neutrino mass. I think it's very exciting. How to deal with nuisance parameters is a challenge. We need, I think, methodology there. I mentioned two projects close to my heart, but they're only 2 out of a dozen or so. But you can see the timeline, DS starting, there's it 2018, and then Euclid after 2020. Maybe the most kind of closing with, again, kind of philosophical remark, are we going to experience another paradigm shift in our lifetime? I feel very fortunate. I came to Cambridge. There was 4% baryons, 96% cold dark matter. And I was told it's fine not to understand one component. And then, again, the history of that does not, by the way, start with supernova. I believe it starts with APM and clusters and so on. The decade before, there was this major paradigm shift. Unfortunately, the young people in the audience have not experienced paradigm shifts, So I wish you to experience it in your lifetime, to actually see that somebody would say, look, it's not lambda, something completely different, and this will also keep theoreticians busy. So thanks very much.
Well, thank you for a great talk and keeping to time. We've got time for questions.
So I wanted to tackle this last point about nuisance parameters and so on. I mean, a lot of observational astronomers have been quite upset with my attitude to their data. But the thing is that there's a very substantive point. We work very hard in Planck to understand our chi-squareds. After fitting, we include the nuisance parameters that we think are actually relevant, and you've no choice about that, right?
Yeah.
You have to include nuisance parameters, and then you have to look at how they couple with cosmology and so on. And so the good thing from the CMB is that there's a very weak coupling, though when you get to quite difficult models that are highly degenerate in the CMB, it starts to become important, and that is a fact of life, and I think it's important that people understand that there are those dependencies there. But with Planck, we got chi-squareds, reduced chi-squareds, very close to unity. We understand our statistics, so on. That's not true of any of the other astrophysical data sets. Okay, so supernovae, no understanding of chi-squareds, no proper understanding of nuisance parameters. Hubble constant, Cepheids, even worse. Okay, and so on and so on. Every data set, astrophysical data set, the chi-squareds, are not understood. And so when we go into the era of precision, further precision, you have to tackle these problems. And then that determines, what you do with nuisance parameters. You have to understand your chi-squareds. And if you don't, then why should we believe them and fold in likelihoods, with anomalous chi-squareds?
So your grade needs attention.
When you talk about the physical motivator parameters to fit different data and everything, also there is a lot of difficulty here because you can choose these parameters quite freely, and even if they are very different, the physical motivation can be the same, but you're going to have really different values.
Right.
There are also many correlations that's going to affect your results. So how to constrain to more or less universal parameters that you can compare with other people?
Well, so there is a formalism. There are some experts in the audience. Model selection, if that's what you're after, if I understood correctly, that you can have, say, dark energy model W0, WA, and modified gravity model with 10 parameters. How do you compare, even if the chi-square happens to be the same, almost, which is how do you compare? So there's a machinery of model selection, which is it's called Bayesian evidence. It's a denominator and Bayes theorem, and there's quite an interesting debate in the literature on how useful that is in cosmology. Okay, formally it's correct. It's also very demanding computationally, but there is a discussion in the literature. So I think that's another issue. Okay, is how to contrast. Should you add, another type of neutrino to your analysis? How would it improve the chi-square? But what's the penalty? So there is statistical literature on that.
Final question, anyone? Okay. Brilliant talk. Thank you very much again.